Okay, we'll study multivariate normal distribution. So, the random vector is a vector of random variables, n-dimensional, and this is definition of expectation, and the covariance is n by n matrix, and whose n by n matrix whose ij element of this matrix is equal to covariance xi and xj, and this is n by 1 by n. So this is x is a column vector, so this should be prime here. So this transpose is on the right side, so it's a typo. Okay, so that is the definition. And the first theorem is easy, just the expectation can take inside. The second part is the covariance matrix, and the covariance matrix is defined to be this way, right? So then if you have A times X, and A is a matrix, any dimension, I mean where the dimension the dimension should match with the multiplication operation. So then using this definition, this is a we have something like this, right? And then A can go outside, and then the right side it becomes prime transpose. Now to study the PDF, to obtain the PDF multivariate normal distribution, we start with the standard normal distribution. So independent normal random variable. So that's the simplest normal distribution. So this is the basically PDF, right? PDF of Ci, which is normal 0, 1, and then because of the independence, we have the product. So this is the PDF of the multivariate normal distribution with this particular form, standard simplest form. And now we're going to use this one to derive more general class, which is a linear transformation of this. So you can notice that in this particular linear transformation, expectation of x random variable should be expectation a times expectation z, right, plus mu, so which is mu, and variance covariance matrix should be a times variance z times a prime. By the way, a is variance z is identity matrix, so this is a prime. So we can call this sigma. So sigma is the variance covariance matrix of x, random vector x, and then we can derive the PDF of x from the PDF of z, and this is the answer. Okay, so we have some kind of transformation inside the exponent, and then we have something here. So this is kind of Jacobian, and this is inside is just a transformation quadratic of the quadratic term. And second result is that the MGF of x is exponential function of this quadratic function. So you can see that if x is a scalar, then it leads to what we know already, right? So we can derive the density. I already wrote it. And so first notice that this is A is non-singular matrix. So to make the life easy, we start with the simplest case where A is non-singular, so that the inverse exists and this transformation is 1-to-1. So this is 1-to-1 transformation because A is non-singular, so the inverse exists, and this is the inverse transformation. So we can simply apply the inverse function theorem using the density of z, and so then this is the result of the inverse function theorem, and just apply. So this is z prime z, right? So this inside the exponential function, this is 1/2. I mean minus 1/2 times z prime z. So this is the density function, and then this is Jacobian. And then we just do matrix algebra, and then so we already defined the sigma equal to a prime. Then sigma inverse is a prime inverse. A prime inverse a prime a inverse, right? So that is a inverse prime a inverse. So that's how we obtain this one. And then also the determinant of sigma inverse is a inverse times a inverse, right? So that's why we have this result. So this one becomes this. So that because of the last result. Okay. So that derives the density function of the normal distribution, multivariate normal distribution. So variance covariance matrix is here, placed here, and then the mean is subtracted, just subtracting the x original vector, right? So that's kind of a way of understanding the density function. Now let's derive the MGF. So I'm gonna derive this one, derive this MGF. So the MGF can be first we should use the we should first derive the MGF of Z matrix. I mean the vector from standard normal distribution, and that is, so this is should be vector. So that this is definition, right? Definition of the vector MGF of vector function, and then this is just a trivial, and then this one is independence. Sorry about that. And then this one is a standard normal distribution, right? Using standard normal distribution, so we obtain the MGF, and then with that we can apply a linear transformation, and so we just use the definition, right? And then simplify, and basically the scalar term can go outside the expectation, and inside this one we just used, I mean this is just the definition, right? And then this one becomes this one, because we can actually call this S, right? Vector X as T. So what is the result? Well, we already know. We use this result to obtain that this is half S prime S, because C is normal random variable with mean 0 and identity matrix, covariance matrix. So we use that, so that means S prime S is equal to T prime A times A prime times T. So, and then the inside, this guy is already defined it to be sigma, so that proves the MGF. Okay, so that's it. Okay, and this is just the explanation of the spectral decomposition. You guys can take a look, but this should be covered already in linear algebra, right?